Okay, it's 2:40. We'll get started. Everyone happy to have the election behind you? Plus you got an extra day of sleep. You could sleep it off and now back to work. So, all right, let's see here. A couple quick announcements. Homework 8, it was going to be due on Wednesday. I'm not going to get through quite everything today. I'll get through most of it, but I'll need a little bit of the next class. So I've already changed the due date in WebAssign. It's going to be due on Thursday at noon, regular time, just on Thursday. And I'll send around an email to that effect as well. And in that email, I'll mention the final exam date, which again is Monday, November 23rd. It will become available and due on November 24th. Available at noon, due at noon. I'll put that in the email. Also, office hours this week will be on Tuesday again, so you can have an office hours before the homework is due. And that's it for announcements. Any questions about anything before we get into the warm-up? Okay, so let's take a look at this warm-up question here. It has to do with tidal forces, which we'll see a lot in this lecture. We've begun to see in previous lectures. So we know the force of gravity drops in proportion to the mass divided by the distance squared. We've seen that many times. Tidal forces drop as mass divided by distance cubed. So the tidal force, with tidal stretching and tidal forces, the force on one side of the orbiting object stronger than the force on the other. And so it gets stretched out. And I'm not going to derive this, but this is just going to hopefully be a testament to how well you can do ratio problems now. I can just throw an equation at you and you should be able to use it in a ratio context. So I'm telling you here at the beginning, the strength of the tidal force that a world feels, a world that's orbiting another, is mass divided by distance cubed. And I've given you the mass of the orbiting object in Earth masses. I've given you the distance that it's orbiting the central body in Earth-Moon distances. So we have Earth's moon on the list. And since the central mass is in Earth masses, the distance is in Earth-Moon distances, we're going to end up with 1 divided by 1 cubed. I'll give you that one. So that's just 1. So the unit is Earth units, Earth-Moon tidal stretching units. And again, that's the whole ratio approach. It all comes out in the units of the comparison object. So what else do we have in this table, though? We have Mercury going around the sun. So they're not all moons. I have one planet with the sun being the central object. And so we have the mass and the distance here in the Earth and Earth-Moon units. For Jupiter, I have Io, which is the closest in of the Galilean satellites, which we talked about last time. And I have Callisto, which is the farthest away of those 4, which we'll talk about this time. So same central mass, but different distances. And I also have the large moon going around Saturn, Titan, and the 7th large moon in the solar system, Triton, going around Neptune. And we haven't spoken about those yet, but we'll get to those next time. Anyway, for each one of these, I want you to calculate the tidal force and then pick out the strongest and the weakest. Combine those two and submit a 2-digit number. And since there are a lot of calculations here, I'm going to break you into groups and give you like a minute and a half. You can split them up and check each other and then come back and submit your answers. So let's see, I got 27 of you. I'm going to put you into five breakout rooms. Let me set that up. Looks a little different. Let me open it up, make sure you all have been assigned. Oh, 1 second. Assign automatically. Okay, and I'm going to open the rooms and I'll give you a 60-second warning. Oh, and you may want to take a screen capture before you go.
Are we supposed to be in breakout rooms right now?
Yes. Yep.
Do you mind assigning me to one? Sorry.
Oh yeah.
Thank you.
Okay, everyone's back now. Should be. You're coming back right now. Yep. Okay, so go ahead and submit your answers. See if we get any more. Okay, 15. You can keep adding them, but let's take a look at what we have. And yeah, let me just make sure there nothing else in there. But yeah, most of you got it right, 31, 3-1. So let's take a look at the numerical responses. Same table here, just with an extra column where I have mass divided by distance cubed. I guess I used the letter R, meant to use the letter D, but you get the idea. M divided by D cubed in this column. Again, oops, 1 second. There we go. Again, for the Earth-Moon system, it's 1, 1, and 1. So everything's relative to the tidal force felt by the moon. Mercury comes in the lowest, 0.098. Even though it's going around the sun, and the sun is supermassive, it's far enough away. Again, tidal forces drop pretty quickly with distance, faster than the force of gravity drops. So it becomes kind of minor, but it's still enough to create the 3-2 spin orbit resonance that we talked about, kind of the locking of the orbital speed and the rotation speed when the planet Mercury is as close as it gets to the sun. So stronger with the moon. Then out here going around Jupiter, we have the 4 Galilean satellites, Io the closest, Callisto the farthest. With Io, it's 240 times, and that's the strongest of the ones here. As we saw last time, the tidal force, and combined with the other moons disrupting that tidal force, causing tidal heating, is very powerful. It's enough to melt the mantle and create this volcanic world. But as you move your way farther and farther out to Callisto, it drops off and it's only 3.3 here. And we'll see the tidal forces here. It's enough to tidally lock the world, but we won't even see much tidal heating in this case. Titan going around Saturn, similar, and then Triton going around Neptune, a little bit higher. It has kind of an interesting tidal history and tidal future that we'll get to in the next lecture. Okay, so very good. And again, this is just to show you that you've gotten really good at doing these ratio problems. I just threw an unfamiliar equation. We never derived this one. I just said this is what it is, run with it, and you're able to do a bunch of calculations quickly and get the right answer. So very good. Okay, so last time we were wrapping up Jupiter. We'd gotten through the planet and gotten through half of the moons, Io and Europa, half of the Galilean satellites, Io and Europa. So we'll begin today with Ganymede and Callisto, and then we'll move on to Saturn and get as far into Saturn as we can today. Again, I'm going to be going at a good clip, trying to catch up before the end of the semester. But if I say anything confusing, just stop me, or if you have any questions, just shout them out. Okay, so let's see here. Again, here we have our planetary system, Io, Europa, Ganymede, Callisto. We're up to Ganymede. It's farther away, so the tidal force will be weaker. We're not going to see, for example, with Io, we saw the volcanic surface caused by tidal heating. With Europa, we see the cracks in the surface caused by the tidal stretching. On the ice surface, we're going to see less and less of that the farther out we go. The other big difference is the density has dropped. For Io and Europa, the density was in the 3000s. So that's kind of somewhere between the rocky metal interior and ices and water. And as we go out to Ganymede, Callisto, it's down below 2000. So this means we're going to have even more water, a higher, larger amount of water built into it. So the interior of Ganymede probably looks something like this based upon the density. Kind of like the interior of Europa, where we have the solid iron core and the solid rocky mantle. We probably have those things as well with Ganymede, except we have a lot more water bringing down the density. And that's a tremendous amount of water. If you remember back to Europa, even though it's a small surface area world, that's a very deep ocean. That's 100 kilometers deep. And there's twice as much water there on Europa under the ice surface as on Earth altogether. And so if that's twice as much water as Earth has on its surface, this is just a humongous amount of water. Though, as you'll see, it's probably not all in a liquid state. Was in the past, but it's probably been freezing. It's probably not completely frozen, as we'll see. It's something we call a slush, something between a fluid state and a solid state. Okay, so let's jump into, well, that's the interior. So let's move on to the surface. That's what we know about the interior. It's kind of limited based primarily on the density, but pretty reasonable. Surface we can tell more about because we can see it and take more data on it. And we see a mixed surface. We see some darker regions and some lighter regions. None of the regions are as light as Europa's surface. If I go back here, we see how bright this ice surface is. And all these worlds, Europa, Ganymede, Callisto, they're covered in ice, but clearly they're very different shadings. Very bright ice on Europa, very dark ice on Callisto, a mixture of shades on Ganymede. As I think I might have mentioned, the color that the ice appears depends on how old it is. The longer it's exposed to space, the more dust accumulates on it, the more micrometeorites darkening it. So the fact that none of the ice on Ganymede is as bright as Europa tells us the surface is a little bit older. On Europa, with all those cracks and water always pouring out of them, we keep a pretty fresh surface. So that's not going on with Ganymede. Though we do have regions that are darker and lighter, and it's kind of reminiscent of Earth's moon. With the Maria, we have these dark regions, which, if you recall, caused by impacts that cracked far enough down that this basaltic rock came up in the form of magma or lava and filled in low-lying areas and solidified, creating these dark spots on the moon. Same idea here on Ganymede, except it's not basaltic rock, but ice. And so the Maria are actually the light-colored regions. It's all ice. And you have the old ice, and you know it's old because it's gotten pretty dark. And then you have the lighter regions. What we think happened is something hit the surface, punched through, and water poured out and refroze. and then you had a fresh surface. And so the Maria on Ganymede are the lighter regions, and these darker regions would be like the analogous to the Lunar Highlands, I guess, older. Also confirming that is craters. We can look in these regions and count the craters, and there are a lot more craters in the dark regions than the lighter regions, which again suggests the lighter regions are newer, but not brand new. They're pretty old as well. Now, if we focus on the dark regions, we see a feature in them that we don't see in the light regions. So if we zoom in to one of these dark regions, we see these creases. Again, these are not like the cracks on Europa, which are caused by that tidal stress. Again, I said, imagine taking the squishy ball I had last time, dunking it in water, putting it in the freezer, and then doing that to it. You get cracks all over it. This is farther away. We're not going to get tidally induced cracks like this. What we think these are is plate tectonics. We think in the past that water underneath was fluid, and you had ice, you had plates, but made of ice floating on the surface. So kind of like on Earth, where we have rock plates on a rocky mantle that's minimally fluid, but it does flow. In the past, you probably had ice plates on liquid water floating around, running into each other, crunching, creating these creases. So it's, again, interesting parallels, very different places, but similar processes at work, different materials, the same idea. Now, we don't see these in the lighter regions, which means this process kind of came to a conclusion. And we think just the interior cooled down and that gigantic ocean solidified, at least partially. In which case, things aren't going to be moving around on the surface anymore. You get locked into place, kind of like Mars being geologically dead. The surface is not moving around. Now, we don't think it's frozen completely because we've flown by it with the Galileo spacecraft. And just like we saw with Europa, you get that secondary magnetic field. The water is salt water. It doesn't make its own magnetic field, but it interacts with Jupiter's. Jupiter's magnetic field interacts with it, producing a secondary magnetic field that the spacecraft can measure, but only if it's fluid. And we have measured that with Ganymede. So it's not completely icy. There is still some motion in there, just greatly reduced compared to what it used to be. Okay, so that's Ganymede. And then Callisto is pretty straightforward. It's really far from Jupiter. It's tidally locked. There's enough tidal forces to lock it, just not really to heat it. And well, first of all, you can see on the surface, it's very dark. So it's very old ice. That means it became inactive geologically. If you want to think of the behavior between ice and water is geological activity, but it became inactive a long time ago. That surface just kind of stayed put and got dirtier and dirtier, except where you have occasional impacts that clear off a little bit of the ice or melt a little bit of the ice, refreshing it. Makes it really pretty. I think it's the prettiest of the large moons or of the moons in the solar system. Here's the biggest feature on the surface. It's an impact crater, sort of. It's more like an impact crunch. Something big hit it, and it just kind of crunched or compressed. Not your traditional crater called Valhalla. And this is not surprising given what we think about its interior. It formed, and it probably formed not super hot, and there wasn't a lot of tidal heating to keep it hot. So it probably never even differentiated on the inside. The differentiation, as we've talked about and seen in many cases, every case so far, all the worlds we looked at, as long as it's fluid on the inside for a long time, the heavier stuff sinks to the bottom, the lighter stuff floats to the top, and then parts of it can solidify and sets the various layers that we see here and all the other worlds we did. Callisto, the experts think it never got hot enough to be liquid on the inside. And so it's kind of like one of those, like a mean kid snowball, not like an ordinary snowball, but the mean kid, he gets the gravel. And I did this a couple times myself. So I guess I'm a little mean on the inside, I don't know. But the snowball with all the gravel and rocks in it, that's kind of what Callisto is. Now, the surface is, the very topmost layer probably did differentiate. As you get those impacts, it does melt little regions, and that allows those regions to differentiate. So you probably have surface differentiation, but the interior is probably a mixed ice rock, composite. So those are the 4 large moons of Jupiter. There are no medium-sized moons. We'll see with the other worlds, they do have medium-sized moons. And the 4 large moons are in close. They formed there, and we'll learn in lesson 9 how that happened. And then you have all these other moons scattered all over the place. These are small moons, and they're all captured asteroids. Just like Mars. Mars captured those 2 asteroids, Phobos and Deimos. All these are just captured asteroids. And sometimes we know that for certain because they're orbiting backwards. If something's orbiting backwards, it did not form there. Everything forms going around the same way. Other ones orbit in the forward direction, but they were probably captured as well. The orbits are very eccentric. When things form naturally, they form in nice circular orbits. This is just a mess of things. It's very close to the asteroid belt, and Jupiter is very massive. So Mars is massive enough to pull 2 of them in. Jupiter has pulled, 70, 80, 90 of these in. We keep finding more and more of them. Last slide for Jupiter. It also has a very thin, wispy ring. We didn't even know about it till we flew by with the Voyager spacecraft, but I'll put that off. I'll talk about rings in the context of Saturn, which has the biggest, most impressive ring and system in the solar system. So we'll come back and address that later. But any questions about anything with Jupiter before moving on to Saturn? Okay. So Saturn's next. And let's start by talking about its tilt and actually having a digression and talking about the tilts of all the worlds. We've been noticing the tilt. Some worlds are tilted, some worlds are not. We've offered some explanations along the way, but let's kind of spell out the different categories. For example, here we see Saturn is tipped 27 degrees. That's hard to do with a world this large. It's not easy to tip over these massive worlds. But let's go to the dot cam and spell out what the different categories are. Maybe I'll make it full size. Okay, so, and this will probably be the subject of tomorrow's warm-up question. Different causes of planetary tips. So let's write down 3 categories. You can have small planets with no large moons. You can have small planets with a large moon, such as Earth. Earth is a small planet with a large moon. And 3, then you can have big planets. So these are the 3 basic categories. And maybe over here, I'll make another column telling you what happens to the tilt. So let's start with small worlds, small planets with no large moons. Their tilts wander with time. I'm talking about worlds like Venus and Mars. They're small worlds, no large moon, which we'll see as a stabilizing influence as it has been with the Earth. They wander just as different things tug on them. Maybe Earth passes by and tugs on either Venus or Mars, or Venus or Jupiter or Saturn comes to closest approach and tugs on them. These little random tugs, and random's the key word here. There are 2 different types of tugs you can have. You can have random tugs that occur at random times, and you can have resonant tugs that always occur at just the right time. It's kind of like pushing a swing. We'll see. If you push a swing at random intervals, it just jostles around, doesn't really go anywhere. If you always push it at just the right time, the little pushes can add up into a big effect. Anyway, small planets with no large moons to stabilize them, they get all these little random tugs from all the different worlds in the solar system, and their tilt can wander with time, can even flip over. That's another explanation for why Venus might be going backwards. Maybe it's flipped completely over. Its rotation was never reversed. It's just its orientation was. Anyway, they wander. Now, if you have a small planet with, oh, I should say Mercury. Mercury's a small planet with no moon, but that's a special case. It's close to the sun. It has that, not the tidal locking, but the 3-2 spin orbit resonance. So it's stretched out, and that elongation wants to point towards the sun. So because of the tidal forces, the rotation axis, as we talked about, is always perpendicular. Its tilt doesn't wander. It's locked in by the sun. So it's a special case. But anyway, small planet with a large moon, that's like the Earth. Once you have a large moon, it holds that tilt in place. Our tilt is 23.5 degrees, and it varies between 23 and 24, but not any more than that. And it's because of the complicated gravitational interactions with the moon, locked it in. Originally, we were straight up, and as we talked about, probably something big smacked us, knocked some material off that formed the moon, and that impact tipped us over. But once that moon solidified, it held the tip in place. And then you have the big planets. And little gravitational tugs don't affect them at all. They're big, they're massive. At least little random gravitational tugs don't. If you have a tilt, so I should say big planets, you have no wandering. And small planet with a large moon, also no wandering. But the big planets, some of them are tilted. As we saw, Saturn is tilted. Uranus is flipped on its side, not all the way over, but like 90 degrees. Neptune has a lot of tilt. Jupiter's tilted too, a little bit, 3 degrees. Anyway, if the tilt is not 0 degrees, there are two possible explanations. One is an impact, which should not surprise you at this point. We've seen major impacts with all the worlds. As I've said before, probably we had twice as many planets originally as what we do now, and that probably goes with the gas giants too. You probably had gas giants running into gas giants, and that can tip them over. Jupiter was tipped a little bit, Uranus and Neptune a lot. Saturn's tip is different though. You can have resonance. Again, it's the opposite of these little random gravitational tugs. These are where you're pushing always, or tugging, as the case may be, always at the right time. Saturn, there's a resonance between Saturn and Neptune. They're in a position that, like every other time, one of them comes around, the other's there, tugging on it in just the right way. It's kind of a subtle resonance. I won't get into the details. I'd have to look some of them up. But basically, very slowly over the billions, the 4.5 billion years, Neptune has been tipping, words not coming out today. Neptune has been tilting Saturn over slowly, more and more and more. It's now up to 27 degree tilt. So that's kind of like the general summary of all the different things that can tip and tilt planets. Questions about any of that? Okay, let's go back to Saturn then and see the effect of this. So here's Saturn tipped over by resonant gravitational tugs with Neptune. And it means sometimes when we look at it, we're looking at it edge on. And sometimes, like here and here, if it's tipped like this, we're seeing over the top of the rings. If it's tipped like this, we're seeing underneath. Here's a calendar showing how Saturn appears throughout the years. Last time we viewed the rings edge on was 2009. The next time will be 2025. So if we find the glorious year 2020, here we are. If you're in the lab course, your pictures probably look something like this. You're viewing over top of the rings and have a pretty good view of the rings. Let me see what's next on my slide deck. Right, yep, okay. So this is just a picture of Saturn as viewed from Earth, looking through Earth's atmosphere. This is about as good as you can do. If you're in the lab course, you took black and white pictures, somewhat like this. We have bigger pixels on our cameras, but something like this is what you should have been able to see. Now, if you go to Saturn, so this is taken by Cassini, and I think it's one of the most awesome solar system pictures out there, taken by Cassini as it was approaching Saturn. And it looks fake, but it's a real picture. Just that's how it looks once you get up close to it with the high resolution camera, majestic and all that. Let's compare Jupiter and Saturn, so bulk properties. Go back to our table here. So Saturn, we can see it's just a little bit smaller than Jupiter. Not the rings extend out farther than Jupiter, but the planet itself is a little bit smaller, 9.5 Earth radii compared to Jupiter's 11. But the mass is a lot less. It's about 30% the mass of Jupiter, clocking in at 95 Earth masses. And so then we can calculate our three favorite things: average density, m over r cubed; surface gravity, m over r squared; and escape speed, square root of m over r. And we see with the average density, it's still in the ballpark of 1,000. It's a little bit on the low side. And so the gas is not super compressed. It's a little bit more spread out. And since it's lower than 1,000, remember the density of just ordinary water is 1,000 kilograms per cubic meter. So if I had a bathtub big enough to hold Saturn, and there's some kind of gravitational field defining up and down, Saturn would float in such a bathtub where the other gas giants would sink. Just a meaningless factoid. There is no such bathtub out there, of course, but it's slightly lower density. Surface gravity, comparable to Earth. We talked about this before. Saturn, Uranus, Neptune, they have Earth-like surface gravity. Of course, that's at the cloud tops, not down at some rocky core surface down deep down underneath. And Jupiter is much higher, 2.5 times. And this will explain, we'll see the big variation between the worlds, their surface appearance. Jupiter with all of its detail and color, and Saturn with its kind of bland, uniform butterscotch will tie it to surface gravity. Then you have the escape speed, and Saturn's is a little bit lower, but still enough to hold on to the hydrogen and helium, which is the most abundant of the stuff out there. So that's what you need to be able to hold on to be a gas giant. Plus it's farther from the sun, so it's cooler out there. And that also makes it easier to retain your atmospheric elements, hydrogen, helium, and then the water, ammonia, methane. Okay, so those are the bulk properties. Let's see what's next. Yeah, so the interior, as usual, inside out. And so same trick we did with Jupiter. It's a rotating ball of gas. If it were pure gas, given the speed that it's rotating, it would get somewhat oblate. And we can measure that oblateness, and it's pretty big. It's 10%. Jupiter, as we saw, was only 6%. This is 10%, but it's not as big as it would be if it was pure gas. So again, we can conclude there is a rocky, icy, probably some metals in there too, core deep down inside. The modeling gives this kind of division of the components in the interior, the layers. Jupiter up here, Saturn down below. Again, you have that rocky, icy core, and there are probably some metals in the rocky core as well. And above that, you have the hydrogen in helium and water, ammonia, methane. Now on Jupiter, remember we divided the hydrogen into two parts, molecular, and you didn't have to go very deep down to hit the metallic. If you squeeze the molecular hydrogen enough, it becomes conductive. The electrons can hop from molecule to molecule. And we saw with Jupiter, we have a tremendous supply of metallic hydrogen, which generates the magnetic field. With Saturn, lower surface gravity, so you got to go a lot deeper down before you have enough squeezing, enough pressure to hit that metallic hydrogen. But there is some there. And it, like all the gas giants, is a rapid rotator. So I won't even ask you this time because I've asked with every planet and you've answered correctly every time. So I know you get this now. We have a conductive fluid layer. It's metallic hydrogen. With Earth and the terrestrial worlds, it's liquid iron. Here it's metallic hydrogen. Rapid rotation churns it up and gives us a magnetic field. In the case of Saturn and also Uranus and Neptune, it'll be about as strong as Earth's. Nothing comparable to Jupiter's, which has all this material to work with. But, you know, Earth has a strong magnetic field, so Saturn will have a Rory. And here you see it in the ultraviolet, and here's Jupiter on the left. And the last bit of the interior is the interior heating. And let's do this as we did with Jupiter. Go back to the dot cam here. So we're talking about Saturn now. And the temperature that we measure on the surface is 97 Kelvin. But the temperature that we should get using our temperature equation, which you're quite familiar with now, it's a rapidly rotating body, it's well atmosphered. So given its distance from the sun and its albedo, we can calculate its temperature, and it should only be 74 Kelvin. And both of these are freaking cold, right? But there's more warmth on the surface than there should be, so there is an internal source of heat. How much extra energy is it producing? Well, again, Stefan's law, energy flux is proportional to temperature to the fourth power. So we do 97 over 74 to the fourth power. That's about 3. So with Jupiter, it's 2. With Saturn, it's 3 times as much energy is coming out as is coming in from the sun. You can see that in this picture. Here's the sun energy coming in and coming back out in the infrared, but 3 times as much. So there's an internal source of heat. And I said with all the gas giants, the story is different here. With Jupiter, it was due to heat of formation. Yeah. All planets form hot, and the larger the world is, it can retain that heat. And Jupiter, being the largest world, still has its heat of formation, its baby fat. Saturn is smaller, and you can run through the detailed physics, and it should have lost that by now. So this is not leftover. It's not latent heat of formation. It's something else. And what's causing it is actually differentiation. It's strange how these same concepts keep coming back and can explain such a variety of things. So differentiation. Saturn is far enough from the sun, cool enough out there, that the helium should liquefy. Right now, it should be liquefying, forming helium drops, raindrops, that then fall down to the lower layers. Remember, differentiation is the process where denser stuff sinks and lighter stuff floats above it. As that helium liquefies, it's a dense little drop and it falls down. It's cold. It's got to be really cold to liquefy helium, but it picks up kinetic energy as it falls. And it strikes those lower layers with that force, transferring that energy of motion into heat. So even though it's freezing raindrops of liquid helium, it's warming the interior. And that will go on as long as there's helium to rain out of the atmosphere. And eventually the helium will rain out, and this will stop, and it will settle into, you know, a temperature of 74 degrees. But while it's going on, this heats it. And we know it's going on because we've taken spectra of the surface, and there's less helium there than Jupiter. So, you know, how much helium is on the surface with Jupiter and the sun? It's about 14%. If you take a spectrum, you find about 14% helium there. In the case of Saturn, it's about 7.4%. So about half as much. It's moved out of the surface layers and it's sinking lower down. And in the other worlds farther out, we're going to see this with the water and the ammonia and the methane. They eventually sink down too. Okay, so that's the interior. Let's quickly do the surface in the beginning of the rings. I want to get to the same place as I did the other class, so we may go a minute or two over. So the surface, we look at the surface here, and as I said before, Jupiter's surface is really intricate and varied in different shades of brown. And on Saturn, it's kind of bland and uniform and butterscotch. So why is that? Well, the cloud layers are the same. Here's the plot you saw before with Jupiter, and here's Saturn. And I've done it to scale. So here's 0, the cloud tops. Here's 100 kilometers down, 200, 300. And you have the same cloud layers, ammonia ice, ammonium hydrosulfide ice, water ice, and beneath that you have the hydrogen, helium, water, ammonia, methane mix. So it's the same structure. The difference is that surface gravity. Jupiter's is very high, 2.5 times as high as Saturn's. So those cloud layers get squished really thin. And sometimes you can see through it, through breaks in the cloud layers. You can see down to the next cloud layer. And the deeper down you look, you see different colors because there are different temperatures, different chemical reactions involving sulfur. Gives you that intricate, varied coloration. But on Saturn, you have less surface gravity. So the cloud layers are very thick and poofy. And you just can't see through that first one. You may have a break in the top, but you just see down to more of that cloud layer. And that top cloud layer is ammonia ice. And at these temperatures, ammonia ice is butterscotch in color. So that explains why it's so uniform. You still see a bit of a banded structure due to slightly different temperatures, but not the detail here. All these different colors are peering down to different layers. So that's tied to the surface gravity, as is the magnetic field, the amount of metallic hydrogen you get. But even though we can't see it as easily, you still have zones and belts. Here's an infrared picture of Saturn. I think this was taken with Hubble. And so you can see, but let me check my notes because I always get them backwards. The zones are high and cold. The belts are low and warmer. And so you can see the temperature variation. It's there. And actually, even though you can't see all this stuff going on Saturn, it's the more violent in terms of weather, in terms of wind. It's because of that internal heat. You have 3 times as much coming out. In Jupiter, it's only twice as much. And this extra heat will kick up the winds. On Jupiter, well, if you look at these charts, it's showing the wind speed. It goes back and forth because, each band and zone goes in opposite directions. But the fastest speeds you get around the equator, it's about 400 kilometers an hour for Jupiter. But with Saturn, it gets all the way up to 1,500 kilometers per hour. So I think these are the fastest winds in the solar system. Also, if you work your way out to the poles, with Jupiter, it gets down to 0. And the same with the southern pole here. But the northern pole of Saturn, it doesn't. That means you have a permanent storm going on up there. Here's a picture of it, a permanent North Polar hurricane on Saturn. And I even have a little animated GIF here. These are probably 10 images taken and put together. You can see it circulating. It has this weird hexagonal structure. And scientists are still trying to figure out why that's the shape that it assumes. They've seen similar things on polar storms on Venus as well. So violent weather. And we have the spots as well. Zones, belts, and spots, right? And the spots are the hurricanes. Again, they're very hard to see because all the layers are the same color. This is color enhanced Hubble Space Telescope image. And we do see spots. These are hurricanes. And right where you have the great red spot on Jupiter, there is a big massive storm on Saturn. Really hard to see because, again, it's exactly the same color as the gas around it. It's called the Dragon, and there it is. And you also get temporary storms. The Dragons, it may be permanent. We don't know. But this is an example of a storm that was temporary. It kicked up a couple years ago, lasted about a month or 2 before it fizzled away. Again, just that extra internal heat is driving some pretty violent weather on Saturn. Okay, questions about the planet before I move into the rings. I want to get about halfway through the rings in our final few minutes. Okay, great. So picture from the ground, we can see 2 rings. It's called the A ring and the B ring, and the division between it's called the Cassini Division, discovered by Cassini in the late 1600s. But here's a picture from Voyager. Once you get up close, you can see the rings have a lot more to them. There are some darker rings farther in that we call C and D. There are other rings, E, F, G. You can see the F ring here. The other ones are farther out that we've only identified by getting up close. And even within the rings, there's a lot of structure and detail that requires some explanation. But first, we should talk about how the rings form. And it's, again, tidal forces, tidal stretching, which we started with our warm-up question today. This figure is a little misleading. It looks like this moon is just free falling into the planet. That's not the intention. Imagine a moon orbiting a planet, and slowly over the years, it gets closer and closer and closer. As it does, the tidal stretching will get greater and greater and greater until eventually you can break apart. And there's an equation for that, a rule of thumb. I'll just put it up here. Let me go to the dot cam. It's called the Roche limit. Once you get within 2.5 times the radius, that's when moons tend to fall apart. The tidal stretching, the gravitational difference from one side of the moon to the other is so great, it tears it apart. Now, this assumes that the density of the moon is the same as the density of the planet. If it's a little bit less dense, it will fall apart farther out. A little bit more dense, it can get a little bit closer before it falls apart. But this is the rule of thumb, works in most cases. And I'll show you some examples here. This is Phobos, which is the moon that's closest to Mars. It's not in the Roche limit yet. It's moving closer to Mars each year, but you can see the tidal stretching. You see the stretch marks going from one side to the other. So this picture is pretty impressive. You can really see gravity trying to tear this moon apart. And someday it will succeed and Mars will have rings for a while. Here's another example. This is the comet Shoemaker-Levy 9. On its second to last journey through the solar system, it passed through Jupiter's Roche limit and got torn apart as it did. And then it broke into all these different pieces and it came back around. And on its last time through the solar system back in 1994, it actually hit the planet piece after piece after piece. It's before most all of you were born, but I was an undergrad then. And it's pretty cool to watch these things just plow into Jupiter, wondering what Jupiter would do. Turns out it didn't do much, just absorbed them. But again, that doesn't form rings. It's a moon. If it gets too close, breaks apart, forms rings. The rings of Saturn were probably produced by a medium-sized moon. Not even a large moon, just a medium-sized moon that was inching its way towards the planet, got too close, and broke apart. And those rings won't last forever. Eventually, the rings do disappear on a timescale of about 100 million years. So that moon got too close within, the past 100 million years or so. Here you can see all 4 gas giants, all scaled to one of their radii. And so this red line corresponds to 2.4 times the radius of the planet. And you can see all the rings fall within that boundary, except Adam's ring, which is a ring of Neptune. It's just a little bit outside of that boundary. That's probably a moon of lower density, broke apart early. What are the rings made of? Whatever that moon was made of. So probably ice for the most part. And so we think the rings are a bunch of like dirty snowballs that have gravitationally clumped together. And we can figure out how big they are. The smallest ones are only millimeters across. The biggest ones are 10, 20 meters across, kind of the size of the auditorium we would have been in if it wasn't for COVID. And we know that not because we've never gotten a close-up picture. This is an artist drawing, but we know that by looking at Saturn in the radio. The wavelength is bigger than the snowball, it passes through. If it's smaller than the snowball, it gets blocked. And so by looking at Saturn at different radio wavelengths, some of them millimeters, some of them centimeters and meters, we can figure out the distribution of sizes. Again, they go all the way down to sub-millimeter and up to tens of meters. Now the rings are super thin. I'm going to play a movie here. This is a ring crossing of one of the Voyagers. It'll kick in a second. So it's approaching and it's going from below the ring plane to above the ring plane, or vice versa. I can never really tell the perspective on these. And you'll see how thin it is. You'll see a few moons going across too. These rings are hundreds of thousands of kilometers across, but super thin, as you just saw. They're only tens of meters, not tens of kilometers, tens of meters. Again, the size of the auditorium we would have been in, thick. So the reason for that is there's this process that can decrease the inclination of these orbits. So suppose you have a snowball coming around here on an inclined orbit, and it's going to cross the plane. Well, maybe on its first cross, it goes through one of these holes and just continues on, and then it will circle around and it has to cross the plane again. Eventually, it's going to be smacked by something in the ring that's going to propel it forward. And it may not be perfect on this first smacking. You may have to go through the rings a couple times, but eventually everything gets pushed into the plane. And so there's no process that thickens the rings. They just get thinner and thinner until they're the size of the biggest chunks, tens of meters. That's why they're so thin. And the last topic, and again, I apologize, I'm going to go a few minutes over just to stay in place with the other section, is the structure we see here. And let's begin with the Cassini Division, this dark region between the A ring and the B ring. What causes that? Well, the Cassini Division is caused by, no, that's the Death Star. It's not caused by the Death Star, it's caused by Mimas, which looks exactly like the Death Star, which is kind of interesting. This picture was taken right when George Lucas was developing Star Wars, the initial movie. So I wonder if this is where he got the idea. But anyway, you have this moon Mimas that orbits just beyond the rings. And anything orbiting at this distance from Saturn, where the Cassini Division is in resonance with Mimas. It's a 2-1 destructive resonance. What's that mean? It means for every time Mimas goes around once, anything orbiting here goes around twice. So you get, it's like pushing the swing. Imagine a particle coming by, Mimas pulls on it. And then it goes around again. Well, then Mimas will be on the other side, but it goes around again and Mimas is here in the exact same position. So it pushes the swing at just the right time, pulls it again. If you're orbiting at any other distance, the pulls won't always be in the same places, same directions. It'll be kind of random all over the place. But stuff in the Cassini Division has this 2-to-1 resonance. It pulls it out into the ring where whatever got pulled out gets smacked by something orbiting out there and the orbit circularizes. So things get pulled out of the Cassini Division by this 2-1 resonance with Mimas. So here's Saturn's rings up close. This whole dark region is the Cassini Division. Part of it, called the Higgins Gap, is completely empty. The rest of it is working its way out. But you see all sorts of structure throughout the rings, and these are other resonances, maybe 3-1 with Mimas. Stuff goes around 3 times for every time Mimas goes around once, or 4-1, or 5-2, or 7-5. There are tons and tons of different resonances, and all these resonances with all the other moons. There are a bunch of moons, and it creates all this structure, all these gaps and divisions, except, and this will be the last thing today, these ones here at the edges. There are 2 gaps out here called Encke and Keeler. These are not caused by resonance, but by a single small moon, high enough density that it was not torn apart. It can move a little bit within the Roche lobe. It's living. There's one small moon in each of these gaps that clear it out. So here's the Encke gap. There's a moon here called Pan, P-A-N, that's cleared out its zone. Now here you can see the even smaller Keeler gap. And just recently we found its moon. It took a long time, called Daphis, D-A-P-H-I-S. These are small moons, very small moons. You can actually see the gravitational tidal waves that Daphis is creating as it goes around. So some of these gaps are caused by small moons only in the outskirts. The rest is resonance phenomena. Okay, so next time we'll pick up with the outer rings like F and E and the moons of Saturn, and we'll finish Uranus and Neptune. Okay, thanks a lot.
Thank you.
Thank you.
Thank you.
My pleasure.
Thank you.
Thank you.
Thank you.